Hi everyone, my name is Neha Kardam and this is the fourth lecture on electronic communications. In this lecture we will learn about amplitude modulation transmission. So let's get started. What is amplitude modulation? So the definition of amplitude modulation we have already covered in the previous lecture. So I'll just quickly read it here. And it says a method of impressing information onto a radio frequency carrier signal, and in the amplitude modulation basically the amplitude of the signal is changed in step with the information. Now this slide talks about making an AM signal, and it says to form an AM signal a circuit with a variable gain is needed. The gain of the circuit is controlled by the information signal. A modulator requires a non-linear device such as vacuum tube, diode or transistor. So here, to construct a working AM signal transmitter or receiver, a knowledge of radio frequency circuit principle is very necessary. A complete AM signal transmitter or receiver basically consists of many different stages and hundred of electronic components. And I hope you remember we saw the basic or the simple RF circuit block diagram in our first lecture. And it gets complicated as we go towards the practical transmitter, AM transmitter or receiver. So all these so all the electronic system, no matter how complex they are built on a functional building block or stages, and that block diagram basically shows how the pieces are connected to work together. So here we are going to learn about two approaches to generate an AM signal. The first is called the low level AM transmission, and the second one is called high level AM transmission. So here we have these two block diagrams of low level AM transmission and high level AM transmission. Can you make a guess like what would be here in these blocks? And same here for the high level. What change will be there in the high level when compared with the low level? You can get an idea, take an idea from the block diagram which we did in the first lecture. So some of the components are going to remain same here in both of the block diagrams. Now let's get started with what these two block diagrams can have. So the low level AM transmitter, you see here we have a RF carrier oscillator, and we have a buffer amplifier here, and then modulator, RF power amplifier, antenna coupler, and audio frequency voltage amplifier, and a mic over here. Now, when we compare low level AM transmitter with the high level AM transmitter, we see that in high level AM transmitter we have this extra audio frequency power amplifier, and also we have a radio frequency final power amplifier attached here along with the modulator. So now I am going to quickly go through each of the block, and I'll explain what these are and what their function is. So this RF oscillator which you see here is basically used to provide the carrier signal, and the output of this carrier oscillator is fairly a small AC voltage. It's around 200 to 400 millivolts RMS value. So the oscillator it must produce an accurate and steady frequency, and if oscillation drifts off the frequency, then the receiver will be unstable to receive the transmitted signal without being readjusted. So it is very important to have a constant and stable frequency. And if somehow this oscillator drifts the frequency being used by another radio station, then interference will occur, and this type of condition is like highly desirable. So two techniques are used to stabilize the oscillator, and which is the buffering and the voltage regulation. And for that, here we have the buffering amplifier attached, and this amplifier uh, it is basically used to amplify the signal which comes from the this RF carrier oscillator. And here the oscillations are similar to engine, and for example, if load on engine increases, the engine will respond by slowing down. So similarly, if the current drawn from the oscillator output, which is here, increases or decreases, the oscillator may speed up, or it may slow down slightly. So this buffer amplifier here is relatively a low gain amplifier that follows the oscillator, and it has a constant impedance. Therefore, it always draws the same amount of current from the oscillator. And this also helps to prevent pulling of the oscillator frequency. And similarly, we can use the voltage regulator if power supply is not held constant. And then we have here a modulator, which is a non-linear amplifier. And in low level transmitter, the power levels are low in the oscillators, and in the buffer amplifier, and in the modulator stage. Typically, it will be around like 10 milliwatt. So here, in order for the modulator to function, it needs an information signal, and that information signal is coming from this microphone. And this microphone is one way of developing the information signal, and however, it only produces a few millivolts of the signal. This simply is not enough to operate the modulator. So a voltage amplifier is basically used to boost the microphone's signal, and the signal level at the output of the AF voltage amplifier is usually around 1 volt RMS, and it is highly dependent upon the transmitter's design. And you also notice that the audio frequency amplifier in the transmitter is only providing a voltage gain, not necessarily a current gain for the microphone's signal. The power level are quite small at the output of the amplifier. It will be around few milliwatt of the power. So here this RF power amplifier is normally built with several stages, and these stages basically increases both the voltage and the current of the amplitude current of the AM signal. So we can say that power amplification occurs when a circuit provides a current gain. And in order to accurately amplify the AM signal from the modulator, RF amplifier stage which you see here must be linear. Now this antenna coupler is you see here is basically a part of the last, or we can say the final stage of this block diagram. And it is not really a separate active stage. It is combined with the whole block diagram, and it performs no amplification and has no active devices, but it has two important purpose, and those are first is it is used to match the impedance, and another is it is used for filtering. So those are the two main job of this antenna coupler. For an RF power amplifier to function correctly, it must be supplied with a load resistance equal to that of that for which it was designed, and this may be nearly any value around like 50 ohms would be an good value. And since most antennas and the transmission lines they work on a 50 ohms characteristics resistance, but But what if the radio frequency power amplifier needs to see a smaller value of the resistance, maybe around like 25 ohms? Then what will happen? Then we must use or we not use we must need to transform the antenna impedance from 50 ohm down to around 25 ohm. So here special transformers can be used to match the impedance, and along with that we can also use LC resonant circuit. They also help in matching the impedance. And the other function of this antenna coupler is to provide the filtering. It basically acts as a low pass filter, and this filtering reduces the amplitude of the harmonic energies that may be present in the power amplifier's output. Now, why do these two different different approaches are used to build the AM transmitters when both methods are essentially looks very same? So I'll move on to the next slide, and here is the answer. So actually the answer lies in examining the cost, flexibility and DC efficiency of both approaches. The DC efficiency of a transmitter can be defined by this formula you see here, P out radio frequency divided by P input DC. And for example, suppose that a certain transmitter requires 36 watt of power from a DC power supply and produces 18 watt of radio frequency at the antenna connector. The efficiency of the transmitter in that case will be given by this formula, P out RF divided by P in DC. Putting up the values, and we see that 50% efficiency will come out. So this transmitter converts 50% of the battery power to a useful radio frequency energy at the antenna, and the 50% is converted to heat, or we can say it is basically loss. So it makes good economic sense that to use a most efficient transmitter layout available. High level transmitter has better DC efficiency than the low level transmitter approach. And naturally we would like all our electronic devices to be as efficient as possible, especially in certain cases. Suppose that a transmitter is operated from battery power, as in a like a walkie-talkie, or maybe aircraft transmitter. We would want to get maximum life from the battery, and we would use the most efficient approach possible. So in that case we would go for a high level transmitter. Now here we see two different approaches are used to build AM transmitters, and it says the high level transmitter sports better DC efficiency than the low level approach and is normally the first choice in battery operated AM transmitters and commercial AM broadcasts. So here this is because the high level transmitter is able to use class C radio frequency power amplifiers, which are usually more efficient than the class A or class B radio frequency amplifiers, which require a low level transmitter. Now secondly, it says if efficiency is so important, then why to use a low level approach? And it says the high level approach performs its modulation at the very last stage. At such high power levels, the only practical method of modulation is the amplitude modulation. So this so in other words, we can say that it's just about impossible to achieve frequency modulation or phase modulation in a high level transmitter. The high level transmitter can only produce amplitude modulation. A low level transmitter can generate any type of modulation, your AM, FM or PM. So all that must be done is to switch modulator circuits. Since the power amplifiers are of a linear type in a low level transmitter, they can amplify amplitude modulation FM and PM signals. And the low level method is very flexible when a transmitter must produce several different types of modulation. So this is the method that is generally used. So in summary, we can say that if we talk about low level transmitter, they can produce any kind of modulation, AM, FM, PM, and they require linear radio frequency power amplifiers, which reduces the DC efficiency and increases the also increases the production cost. And if we talk about the high level transmitters, then they have better efficiency. We have already seen that compared to the low level, and they are very suited for battery operation. However, they are restricted to generating only amplitude AM modulation. Now next is oscillator theory. So here we are going to learn about the oscillators. Oscillators are basically the key ingredient in both radio transmitters and receivers. An oscillator is a circuit that converts DC power supply energy into an AC output signal. The frequency of the oscillator in a transmitter determines the carrier frequency. It is important that the frequency produced be very stable and steady. So here we are going to take 3 examples to explain how the principle of oscillator works. First, here you see this A stands for amplifier, and there is some gain in this amplifier, and then we have this B, this is for feedback, and this feedback will also have some gain. So according to our example, we have set the feedback gain. You can see in 3 of them, we have set the feedback gain to 0.1. And input voltage is also same, which is 100 millivolts, and same is here. So input voltage which is going in is 100 millivolt, and the feedback gain is 0.1. The only thing which is changing is the voltage gain here. So we have taken 3 different values. First is when the voltage gain is 9. Second, when the voltage gain is 10, and when the voltage gain is 11. And we are going to see how our this circuit performs based on these parameters. So when your input voltage is 100 millivolts and voltage gain is 9, in that case, if you send input here and multiply with the gain, then you will get here 900 millivolts, and that's what it is here. And that 900 millivolts will be your output, and it is also being fed back through this feedback. And in the feedback, we know that the gain is 0.1. When it is multiplied with 0.1, we see that we got 90 millivolts. So here you will see 90 millivolts, and when you compare this 9 millivolts with the previous input, which was 100 millivolts, you will see that this new input going into the amplifier is less compared to what we have sent previously. So if you keep on giving this keep giving the input, so now the input is 90 millivolts. When it is again go through this voltage gain and comes here, then the input voltage which is received here will again be smaller than the previous value. And that's why I have shown here the oscillation, how they are basically decreasing as the oscillation takes place, and ultimately it will dies out. Now here second example is input is 100 millivolts, feedback gain is 0.1, and the voltage gain is 10. So in that situation, 100 millivolts going in, 10 is the gain, multiplying them we will get 1 volt. Now this 1 volt will be fed back to this feedback and multiply with the gain, which is 0.1. So here we will get 100 millivolts. So now you see here the signal which we have obtained here, 100 millivolt, is the same signal which we sent through this amplifier. So 100 millivolts input, and same we are getting here. So in this example, the oscillations are going to be stable. Whereas in the third example, when the voltage gain is increased to 11, then what will happen? Input 100 millivolt will be multiplied with the gain which is 11. Then we will get 1.1 volts, and that 1.1 volts will be sent to the this gain 0.1. So we will get 110 millivolts. So here you see this 110 millivolts when compared with the input which was sent here, it is higher, it is 110, and previously it was 100. So as you keep on feeding this new input, then you will observe that the value of the input will increase, and that can be seen through this this waveform, that how the oscillations increases. So it is again is not the stable oscillator if it has again something like this. So among three, we see that this is the best way to make an oscillator. Now I'll move on to the next slide. So these are the oscillation conditions required to work properly. First is A and B must be greater than 1 to start the oscillation. So here in this second example, you see if you multiply the gain of this, which was 10, and the gain of this 0.1, this is A and B, multiply, then it should be equals to 0. So 10 multiplied by 0.1, which means it is 1. So at when AB is equals to 1, then you will have sustained oscillation. But in order for your oscillator to work, you need to give higher value. So once the oscillator starts at this value, when AB is greater than 1, then you will put the gain at AB is equals to 1. So for an oscillator to start, the loop gain AB must be greater than 1. If the loop gain is equals to 1, the circuit will oscillate. If it is doing so already, if it is not oscillating, it will not start doing so with AB is equals to 1. It's the same thing. And what will happen if AB is less than 1? You know that the circuit will not oscillate. Now the other thing which is mentioned here is positive feedback, and that positive feedback is also extremely important for an oscillator to work. So our oscillator must also receive positive feedback. Positive feedback means that the signal from the feedback block is in phase with the original input to the amplifier. So you see the signal which is going in here. So this signal should be in phase with this input signal. So here in this figure, you see this circuit is not a very good oscillator at all, but it demonstrates how simple an oscillator can be. And this circuit will produce almost a square wave output unless some type of amplitude limiting is implemented within the loop. But here you can easily see that how it is able to achieve the positive feedback. If you add up these, it will make up 180 degree, which means this feedback is in phase with the input signal which is coming here. So they both are in same phase. I'll just quickly read here. Each of the RC section produces 60 degree at the operating frequency of the unit. The total phase shift in the feedback loop is therefore 180 degree, which satisfies part of the Berghausиan criteria for oscillation, since the op-amp itself provides 180 degree shift. The frequency of oscillation is given by this formula. F is approximately equals to under root 6 divided by 2 pi RC. Now here we are going to learn about the Armstrong oscillator, and there are many different oscillators we will learn about, for example Hartley or Colpitts. So let's first see this. The Armstrong oscillator can be identified by the presence of transformer in the feedback loop. So here we have this transformer. What two function does the transformer perform? So we'll learn about that. So here the transformer which you see here, it basically does double duty in this circuit. It not only controls the amount of feedback, but it also acts as a part of a band pass filter, and I'll explain it first. I'll explain how this whole circuit is going to perform when you do the DC analysis. So I hope you remember in the DC analysis what happens. You'll get the DC power from here, and in the DC analysis your capacitor will act as a open circuit and your inductor act as a short circuit. So if you provide the DC input here, then it will go around here and then it passes through this, and this will be a short circuit, and then from here it will go to the this amplifier, and then the collector side of this amplifier will be connected to VCC, and the current will flow in this way. This will be shorted and the current will pass through from here to here. So here this transformer is basically short circuited in case of a DC, and this will be open circuited. And when you do the when you perform an AC circuit analysis for this oscillator, a technician normally they looks for three important things. First is what provides the gain, and where is the feedback, and what controls the frequency of the oscillator. So gain is basically provided by this amplifier you see here, and the feedback is provided by this transformer you see here. And this transformer, as I said before, that this is going to provide the feedback, as well as this is going to also provide the band pass filter. So you see here inductor and the capacitor makes up the band pass filter, and you know that the frequency the frequency of this oscillator is basically will be controlled by this band pass filter. And this band pass filter can pass only frequencies within its bandwidth, and it rejects frequencies that are above or below its resonant frequency. And this band pass filter is performed by the capacitor you see here and the inductor. So this is the functioning of this Armstrong oscillator, and then the feedback path which will be given through this, you know that the output will be taken from the collector side, and then this part is also fed back to this transformer, and then from here it will be fed back, and then it is again will be sent through the base of this amplifier. So here the Armstrong oscillator is practical up to about 2 megahertz, where its stability is compromised by parasitic resonance in the feedback portion of the circuit. It is often used as a local oscillator in AM broadcast receivers. Identify the gain, feedback, and frequency control. So we know that all these three things. Now moving on to the next oscillator, and this is the Hartley oscillator. Let's first do the DC analysis of this Hartley oscillator, and it is very similar to the Armstrong oscillator. Again, the voltage divider biasing is used here. You see R1 and R2 settings, the base bias voltage of the Q1. This is our Q1 amplifier. So this R3 you see, this sets the emitter current, and again there is no collector resistance here. When we saw here in the Armstrong oscillator, there was no collector resistance. Here also we don't have the collector resistance. The inductor here in this Hartley we have L1, and in the DC analysis this L1 will be shorted, and the collector of Q1 to the positive VCC, it will be connected. So you see here in the DC analysis VCC will be connected, and this will be powered from here and then to the here. This capacitor will be open circuited, and this will be short circuited, this inductor. And then so the full power supply voltage will appear through this across this collector, and then we have power coming from here. Now in the AC analysis, the AC signal will flows into the base from here, and the transistor here you see will cause a 180-degree phase shift, and that will appear across here. And the signal which comes out of here will be the enlarged signal to the collector, and then it will move up to the bottom of this L1 inductor you see here. Since a 180-degree phase shift has occurred in the amplifier, there must be another 180-degree phase shift somewhere in the circuit, so that we have a positive feedback, or we can say that so that we have a 360-degree angle, and which means providing the positive feedback. So because of this, you see here center tap on the L1, there is actually a 180-degree phase shift across its ends. You see here the bottom terminal receives the bottom terminal of this L1 receives the amplifier output from the collector, and the top terminal of this L basically provides the 180-degree phase shift signal for the feedback and going through here. So here you see this coupling capacitor, and it is there to block DC currents between the base of the collector circuit of the amplifier. You might wonder how a technician can tell that that this is the coupling capacitor merely by looking at it. So this can be determined by seeing the value of the capacitor. So the value of capacitor here will be around 0.1 microfarad, and which is very low, which has a very low reactance. It is therefore appears as a short to AC signals. And then we have here a band pass filter. This C and this L is forming a band pass filter, and again it controls the frequency of the oscillator. So this LC tank formed by this L and C is a filter, and only frequencies close to resonance can get through the feedback filter. So the circuit can only oscillate close to the resonant frequency of the LC tank. So I'll quickly read this. A Hartley oscillator uses a tapped coil to obtain its feedback signal. Because the tap is at a ground potential, the end-to-end phase shift around the coil is 180 degree. The placement of the tap determines the amount of feedback. We have already discussed this. Hartley circuit is useful up to 30 megahertz. So this is the important information. Its primary advantage is the simplified feedback circuit. No transformer is required. So you see here we are using the simple circuit here. Center tapped inductor is here, and this is providing the feedback circuit. Identify the gain, feedback, and frequency control aspect of the circuit. This we have already discussed. Gain is provided by the amplifier, feedback by this circuit. It is being provided, and frequency control is provided by the filter. Now next is Colpitt's oscillator, and the Colpitt oscillator uses a tapped capacitor, as you can see here. to obtain its feedback. So the DC operation for this Colpitt's operation basically works similar to the previous oscillators we see. So here in DC operation, this will be shorted and these two will be open. So the VCC will basically flow from here to the collector of the amplifier, and the other portion of the VCC will flow through from here and to the base of the this amplifier. Now here in the AC operation, if we do in the AC operation, you have seen in the previous two oscillators, we saw that the transistor here was operated as a common emitter amplifier with signal going into the base and coming out of the collector. But here this circuit is a little bit different. There are actually no AC signals being applied to the base of the circuit. So this time the transistor is operating as a common base amplifier, and here the output lead is connected through the collector and the input lead is connected through the emitter. And you see the collector AC output flows into the resonant tank. Here from here it flows into the resonant tank formed with this inductor and these two capacitors C1 and C2. So this basically forms a bandpass filter that controls the oscillator frequency. Now you might wonder why two capacitors are used here in the circuit. So the capacitor in this circuit have basically a dual purpose. First, they are a part of the resonant bandpass filter formed with this L, and secondly, they form a voltage divider that controls the amount of feedback. So here you see C1 and C2 make no phase shift. How can this circuit possibly oscillate? So previously, if you remember, in our last two oscillators, we had these transformer and then this center tap coil, which were producing the phase shift. But here with this combination of a capacitor, this does not produce phase shift. So how this oscillator is going to work, because we need to have the positive phase shift. So the answer is you will notice this amplifier. This is a common base amplifier, and common base amplifier produces no phase shift. So we say that so we can say that there will be no phase shift produced by this circuit, and as well as no phase shift will be produced by this circuit. So we can say that the total phase shift walking around the loop is basically 0, and this is a positive feedback, so the circuit will actually oscillate. Now moving on to the next slide, this is quartz crystal, and in order to get the good frequency stability, we use the quartz crystal, and it is often used as a oscillator. And a quartz crystal here is a very precise frequency determining device. It consists of a thin slab of quartz crystal, and it is sandwiched between two metal contact plates. The metal plates are used to establish contact with the terminal of the device. And the schematic symbol you see here is very much looks like a capacitor with the addition of something in between the plates. Now here the quartz, among other natural materials, exhibits what is known as piezoelectricity, or we can say that pressure electricity, which means when a force is applied to the quartz crystal, it bends very slightly. When the crystal bends, the internal atomic structure is displaced. As a result, a small voltage is developed across the device. And increasing the force, what will happen, the voltage will also increase. So basically it is converting the non-electrical quantity into the electrical quantity. Here force or the pressure is our non-electrical quantity, and it is converting into the electrical quantity. Now, some examples of piezoelectric crystals are a crystal microphone, vibration and stress sensor, push button igniter. You must have seen in modern gas grills when the button on the igniter is pressed, a spring-loaded hammer strikes a stack of piezoelectric material. The intense pressure on the crystal stack creates a very short-lived high voltage, which is enough to create a spark of igniting the gas. Now, this piezoelectric effect can also works in the opposite way. What does that mean? It means that if a voltage is applied to a quartz crystal, the crystal will bend a small amount, just as if something is pushed on it, and a quartz crystal can be made to vibrate very much like a tuning fork. So like a tuning fork, a crystal has both a mass and a center resistance to bend or elasticity. So by cutting the crystal to precise dimension, we can basically achieve a precise frequency. And the smaller the size of the quartz slab, the higher the frequency of the crystal we can obtain. And crystals can be made to vibrate in a fundamental mode up to around 20 megahertz. In order to keep the crystal in oscillation, energy must be supplied periodically. This is a perfect job for an amplifier. By applying a positive feedback, we can make sure the crystal will continue to vibrate. So now we are going to see the electric model of the quartz crystal oscillator. So this is the electrical model. You see here Cm is the mounting capacitor, and here Ls is the inductance, Cs is the equivalent series capacitance, and Rs is the equivalent loss. So it appears like we have here a combination of parallel and series resonance. So this is forming a series and this is forming a parallel resonance circuit. So these four elements in the electrical model you see here will be used for a quartz crystal. Now here I'll just quickly read this. All crystals have two primary resonance modes, series and parallel modes. Series resonance is controlled by Ls and Cs. In this mode, the crystal is nearly a short circuit at Fs, and impedance is approximately equals to Rs. Parallel resonance is controlled by Ls and the series combination of Cs and Cm. The parallel resonant frequency is called pole of the crystal. The crystal looks like an open circuit at the parallel resonant frequency. Now we're going to do one problem based on quartz crystal electrical model. So here you see different the values for the capacitor and inductance are given here, and for the resistance. So you will use these formula for resonant series resonant frequency and for parallel resonant frequency, and for total capacitance, and for QS, quality factor. So using this formula you can calculate all these parameters. Now the summary what we have covered in this lecture. So I'll just quickly go through these points. AM signals are created by variable gain nonlinear stages. AM transmitters may be constructed in high or level form. The high level transmitter is more efficient, we saw that, but can only produce amplitude modulation. The low level form can produce any modulation AM, FM, PM, but is relatively insufficient, requires linear power amplification. There are three basic oscillators we saw: Armstrong, Hartley and Colpitts. Most oscillators are derived from these. Crystals provide much better stability for oscillators than LC circuits. Cross crystals have two basic resonance mode, series and parallel, and both are used in oscillators. So this quartz crystal, we will see how they can be used in these three Hartley Colpitts and Armstrong oscillators, and how they improve and provide better stability in the frequency. So this is the end of lecture. Thank you so much for watching.